Now that we know the basic structure of a neural network, we will dig into some detail of how these modeling tools work. Recall our example from last week of predicting ideal mate height. We started with a simple model using only height as an input variable. We then moved on to include the sex of the person surveyed to help improve predictions from our model. The graphs that you see on the screen demonstrate the best fitting lines for the models created for the data that is presented. We will use the same motivating example to introduce the process of creating a neural network. As you will see, several of the steps that we needed to do to build the regression models will be repeated, though may take on a slightly different form than before. As we did before, we will need to import our data into the environment in which we are working, as well as the Python packages that we will be using for modeling. In particular, we will be using functions from the Keras package. Next, we will start creating our model. There are two types of modeling procedures in Keras, the sequential and the functional options. We will start with the sequential option as it is a bit easier to follow. Next, we will add layers to our neural network. In particular, we will start by adding dense layers. These are layers that are fully connected, which just means that each input node connects to every hidden node or output node in the next layer. We will learn about other layers that can be added to our models later in the semester. When we add a layer, we will also need to indicate how many units we want to include for that layer. The units are the number of outputs that we want to come off of that layer. Additionally, we will need to specify our activation function for that layer. Remember, this is the type of transformation we want to do to our linear model as the output moves on to the next layer. Once we're satisfied with our model, we will need to compile it. In this step, we will need to determine what type of optimizer we want to use and the loss function that is most appropriate for our modeling process. Next, we fit the model. In this step, we're indicating that our model is ready to be built. We need to tell the software what the input vector or array will be, the output vector or array, and finally the number of epochs or iterations of training that we want our model to do. This process generally takes a lot of time as we wait for the software to work towards an optimal solution to our problem. Once this is completed, we can print the summary of our model. Let's take a look at some code. To begin, I import the height data into Colab. You can also see here that I need to evoke a function called dropNA on our dataset. In our previous modeling processes with linear and logistic regression, the functions we utilized knew to drop values where either the inputs or outputs were empty. The functions we will be using in Keras don't have that same functionality, so we need to deal with missing data. In the future, you might consider methods for extrapolating missing data values. But for now, we will simply drop any data value in our dataset that has empty values and assume that by dropping these values, we aren't causing any bias in our modeling process. Next, we need to load the appropriate packages to create our model. We will be using a sequential model with dense layers and something called the atom optimizer when we build our model. Each of these functions can be found in Keras under a different subpackage. Now we can start to build our model, which I'm aptly and unceremoniously naming here as model. This model will be built using a sequential structure. Next, we need to think about the appropriate structure for a model. Thinking back to the context of the problem, we want to predict an individual's mate height from their height. When we did this before, we had one slope and one intercept in a linear equation to predict our one output. This tells me that I can add a dense layer that needs one unit, meaning one output of mate height, and a linear activation function, which means I will get my weight and bias in a linear equation that is untransformed. Once we have the structure of our model, we need to determine the measure to be optimized, meaning the loss function and the algorithm that we wish to use to conduct that optimization process. We have seen that the mean squared error is an appropriate measure for quantitative response, which is why I have selected that value here as my loss function. You can also see that I've selected an optimizer called Atom. You can read more about how the Atom optimizer works in the online Keras documentation if you're interested. It isn't necessary, but I've set the learning rate value within my Atom optimizer to be 0.001. This is actually the default value, but you can change it by changing the numeric value within the code that's provided. Finally, we can fit the model. Note that there are 3 inputs to this fit function: the input data, the output data, and the number of epochs. Here I've set the number of epochs to 1,000. As you're building your own models, you will need to play around with this value to determine a reasonable number of iterations to run your training process. After several seconds, the model will finish its designated number of epochs and be ready for predictions. Let's take a look at how our modeling process did. There's more than one method to determine how well our model is doing. We will take a look at one of them here and more of them later. In particular, let's graph the data and the line that's been created through our neural network modeling process. As we did last week, we will need to import matplotlib and create a scatter plot of heights versus mate height values. Additionally, I've extracted the weight and bias from my model. Where did those values weights 10 and weights 000 come from? Weights 10 is the bias of our single node neural network, and weights 000 is the weight. If we look at the model weights, we can see a list of values. In particular, the first element of the list is from our dense layer and is a kernel, or weight value. The second element of the list contains the bias from our dense layer. Simply finding weights 1 would extract all of the information from the bias element of the list. By finding the 0th element of this list, we're able to extract the numeric bias value. The kernel element of this list is different though. You can see that there are double brackets around the numeric value here, as opposed to the single set of brackets around the bias value. We need to subscript with zeros twice in order to extract this numeric element. In general, we will not work too much with extracting specific numeric weights and biases from our model. We're doing it here for demonstration purposes. However, as our models grow in size, it will be very difficult to find specific weights and biases, and they really won't have much interpretable value to us anyway. This code provides us the graph that we see on the screen. This graph has a positive sloped line that doesn't look like it does a very good job of modeling most of the data values. In fact, last week we saw that the line that minimizes the mean squared error is supposed to take on a negative slope, even if it doesn't make sense in the context of the problem. Something isn't quite right about our optimal solution. It's likely that we've reached, or at least approaching, a local minimum of the mean squared error function. You might think that you could just run the modeling process with a different starting location and eventually you would find the true optimal solution. However, I ran this neural network with a random selection of slopes and intercepts dozens of times and never ended up at the location that our least squares regression line did. It's likely that I may never reach the same solution as the least squares regression line. This is one of the drawbacks of the gradient descent process that we discussed in a previous video. It may be the case that I'm bouncing back and forth, completely missing the global minimum that I desire. I could lower my learning rate and let my network run for a long time, and it may eventually reach the desired minimum. In fact, I attempted this with this particular problem and still couldn't find the appropriate combination of learning rate and epochs to reach the desired minimum. A different strategy was needed. In particular, normalizing the inputs and outputs is a strategy to help with the modeling process. In statistics, you should have heard about normalizing by taking the data point minus the mean and dividing by the standard deviation. That is what I've done with the data we have here. This process puts all of the data values on a similar scale, which can be particularly useful when you have inputs that are very different units. You can also do a bin-max normalizing, which just means that you divide by the range of the data instead of the standard deviation. Now when I run my neural network, I arrive at, or at least near, the desired solution. One thing to note about the graph on the screen is that I've gone back to the original units for height and mate height. I was able to do this by extracting the weight and bias from my model and undoing the normalization that I did previously. As far as the modeling process, you'll note that I was able to reduce my number of epochs to 100, which reduced the amount of time that I needed to run my model as well. While normalizing isn't required, it might be a helpful tool when creating your neural networks to get more accurate results and reduce the time that it takes to train your model.